Good evening everyone. Yes, welcome to Get Academy Global. So check and tell me once whether am I audible or visible or not. So check once whether I am audible and visible or not. So I think today there is no problem of light. So the problem has been resolved. Yes, good evening. Okay, so yes, so is it clear now? Yes, Aman, can you mention me please when the digital communication will start? Yes, the digital communication will start today. As I told in the Telegram group that the digital communication we will start today. Yes, Nutan, Pooja, Manish, Lakshmi. Yes, so I hope digital communication I am starting today, so many students may connect with us. So please share it to the other groups. Okay, share the video to the other groups so that many students can come and join the session, because in the last 2-3 days we are not having more than 50 students. So I hope in the today's first lecture of digital communication we will be having more number of students. Yes, good evening Rick. Yes, Rishabh, today there will be first lecture of digital communication. Okay. Yes, audible and visible correctly. Thank you. Good evening, Ritesh. Good evening. Okay, so I think can we start the session? Yes, Dipankar, good evening. Communication will also start in crash course in Gate Academy platform, free lectures which are going. Manmohan, yes, communication will be there also, and that will be taken by Neeraj sir. So that will be taken by Neeraj sir. So he will teach you communication now in main channel in the crash course. So yes, Yashwant, thank you. So yes, I hope you all are enjoying the EMT crash course. Good evening, Sneha. Yes, Shishir, the information theory I will teach. Yes, good evening. Okay, I think now we are having 30 plus students. So yes, sir. Yes, Dipankar. In the crash course, thank you, Gulzar. In the crash course, yes, communication will be taken by Neeraj sir now in the main channel in the crash course. Manmohan, EMT is really good. Thank you, Manmohan. Why crash course available in Hindi? The crash course of the important subjects will come in this Gate Academy Global, but it has been not planned yet. I have already running this crash course in the Global. It may be possible that the EMT subject I will also take in English in Gate Academy Global. There will be a possibility, and there is also possibility that there will be another subject in the Gate Academy Global, but we are not running the complete crash course in the Gate Academy Global because the faculties are same to teach in Hindi and English as well. Yes, Shivani, actually in the digital communication I consider the information theory. In the digital communication I consider 4 chapters. First is the pulse code modulation. Second is that digital modulation technique in which we study about the amplitude shift keying, phase shift keying and frequency shift keying. And the third chapter is the noise in digital communication. And fourth chapter I consider under digital communication is information theory. Thank you, Sneha. You are waiting for the digital communication. So we will start the session now. EMT crash course, like the live session. Yes, in the live session, as I think sir has discussed that in the live session we generally talk with the students, interact with the students. So in that particular time, the time is actually the course will not cover in the limited time. So that is why we don't take the live session live, crash course live. Yes, good evening BRS, Sana. Yes, QAM, actually there is nothing special about the QAM, so Rahul, so that is why you don't need to worry about the quadrature amplitude modulation. There is nothing much detail in the QAM which is going to be asked in GATE. So yes, so we are having now 40 plus students, so I think we should start now. Okay, so here we are starting the very important chapter of the communication, which is digital communication. Okay, so digital communication means whatever will be the message signal, that should be converted into digital form. Okay, so in digital communication we will be having a digital signal. So how do we get the digital signal? Okay, so how can we get the digital signal? So in particular digital communication, if we say, let's consider the first topic of the digital communication. So the first topic of the digital communication is actually a pulse code modulation. Okay, so I am starting it with the pulse code modulation, and in which we will consider each block in detail. Like suppose as I am saying now, right now, so my voice is a analog signal. So my voice is analog signal, so you will be having analog signal here. So this is analog signal. Now this analog signal will be input to the sampler. The analog signal will be input to the sampler. So when we give input to the sampler, it converts the analog signal into a discrete time signal. It will convert the signal into discrete time signal, and that discrete time signal will pass through the quantizer. So this quantizer convert the discrete time signal, discrete time, continuous amplitude, you can also write this continuous amplitude, discrete time signal. So this quantizer convert this continuous amplitude signal into discrete amplitude signal, and it is already discrete time, and the output of the quantizer will go into the input of the encoder, and this encoder assigns a bit to each quantization level. So we will assign number of bits to the each quantization level, and we will get the digital signal here. And this digital signal is converted into rectangular pulse. Here we will get the digital signal. This digital signal will be converted into rectangular pulse, which is called pulse code modulation, which is called PCM signal. So that is done by the line coder. So in this way we convert the analog signal into digital. This is the process, and this is the block diagram of transmitter of the pulse code modulated signal. Okay. So in digital communication, in the first chapter we are having the first topic, which is pulse code modulation. Okay, so in digital communication our first chapter is known as baseband transmission. Okay, so in this chapter, baseband transmission, we are actually transmitting a analog signal converted into a digital signal in the form of rectangular pulse. We are transmitting a digital signal which is achieved by converting analog signal into digital, and that digital signal has been converted into a form of rectangular pulse. Here in this particular chapter there is no modulation. So whatever analog signal will be generated at the source, this is the source, whatever analog signal will be generated at the source, it will be converted into digital signal by these blocks. It will be converted into digital signal, and that digital signal will be transmitted in the form of rectangular pulse directly through the channel. So here there is no modulation. It means that we are not changing the characteristics of carrier signal. The carrier signals are having characteristics like amplitude, frequency and phase. So these characteristics are changing according to the message signal, then it is called modulation. Because in this particular block diagram you can see that we are not even generating a cosine signal. That means we are not even performing a modulation process. So it means because of modulation the height of antenna is reduced, and here we are not even modulating the signal, modulating the carrier. It means that here we are not transmitting the signal by antenna. That means there will be some dedicated wire to transmit the signal from transmitter to receiver. So here the medium will be wired medium. In this particular case the medium will be a wired medium by which we transmit the signal from the channel. Okay, so did you get this point? Tell me, did you understand this point, transmitter, how it process, how it works? We will go to the detail of each block. Okay, so we will go to the details of each block. Just you need to understand what is pulse code modulation. You need to understand only the block diagram of pulse code modulation, and in the pulse code modulation we are having 3 blocks, which is converting your analog signal into digital signal by processing it through the different blocks. So this analog signal is basically a continuous amplitude signal. It is a continuous time, continuous amplitude signal, and this continuous time, continuous amplitude signal can be drawn like this. Suppose this is your message signal. So the voice signal, the speech signal, the voice, the speech signal which we are using is having the this shape, suppose. So it is continuous in time, it is continuous in amplitude. So that is why we are calling it as continuous time, continuous amplitude signal. And after passing this continuous time, continuous amplitude signal through the sampler performs a sampling in the time domain. It discretizes the signal in the time domain. So in this particular point we will get the signal which is the digital version of, discrete time version of the analog signal. In this way we will get the signal. So we will get only the integer values like 0, 1, 2, 3, 4 and so on, -1, -2 etc. So this is t is equal to nts. So we will only get the integer values, we will only get the amplitude at the integer values, because in the discrete time signal we only have the integer values. So in between 1 and 2 there will be no signal present. In between 2 to 3 the signal will be 0. And it is continuous in amplitude. So in the y-axis you are having the continuous signal. After this you will get the discrete amplitude, discrete time signal, and this discrete time and discrete amplitude signal will be having the form of staircase. So after performing a quantization process we get the staircase form. We will see it later. We will discuss it later in detail. How do we get this? So in this particular point, after the quantization, we will be getting the staircase form. So we will be having this staircase form like this, and because this is a staircase form, it is having finite number of amplitude, say 1, 2, 3 and 4. So the amplitude levels are finite, which is 1, 2, 3, 4. So only 4 amplitude levels are there, which can be in the fraction also. It can be 1.5, 2.5, 3.5 and 4.5. Why we are calling it as discrete? Because we are having a finite number of outcome. So here we are having the many amplitudes. It can be anything from 0 to infinite. But here we are having only 4 amplitudes, which is 1, 2, 3, 4. So these 4 amplitude levels can be represented by digital signals or binary signals, binary data. Okay, so we can represent it by binary data. So because the encoder performs the assigning of the code. So since here we are having only 4 amplitude levels, we will be using number of bits 2. So 2 bits are sufficient to represent the 4 amplitude level. So 1 is represented by 0, 0 suppose, 2 is represented by 0, 1, 3 is represented by 1, 0 and 4 is represented by 1, 1. So in this way we get the 4 amplitude levels in the binary form, zeros and ones. So this is called the digital signals. Zeros and ones are called digital signals, binary signals. And now after the line coding, this line coding technique is nothing but a representation of your bit in the rectangular pulse. So in this line coding technique we will consider that the one is represented by a positive amplitude rectangular pulse like this, suppose having the amplitude A, and 0 is represented by a negative amplitude rectangular pulse, a negative amplitude rectangular pulse of finite duration, So we will assign a rectangular pulse to each bit by some technique, and that technique is called line coding technique. So the line coding technique is nothing but the representation of digital signal in the form of electrical signal. So this 0, 0 is represented by this minus A amplitude and minus A amplitude signal of duration TB. Each bit will be having some finite duration, and that duration is called TB. Okay, so this 0, 0, 0, 1 is represented by a rectangular pulse, and that rectangular pulse will be transmitting through the channel. So to transmit the rectangular pulse, how much bandwidth we require, we have to calculate that bandwidth, and according to that bandwidth we consider the bandwidth of this PCM signal. So the bandwidth of this PCM signal we will calculate later. Okay, we can use any line coding technique. It depends on the application. Generally the line coding technique which we use is this one. The one is represented by positive amplitude and 0 is represented by minus A amplitude. Okay, so discrete signal means that will be discrete in time or discrete in amplitude. Any one of the parameter like amplitude and time will be discrete. But when we call the digital signal, it is in the form of zeros and ones. Digital signal means in the form of zeros and ones. So one by one we have to study each block. Okay, so one by one we will study the blocks. So first block is sampler. So we will study the sampler first. So that is why our today's topic is sampling. So sampling is very important, and it is the questions are asked from this particular topic, sampling. Nutan, the line coder is nothing but the representation of digital signal in the electrical signal. Okay, any digital signals like in the form of zeros and ones, it is converted into a rectangular pulse. Rectangular pulse that can have any amplitude, it can have positive amplitude, it can have negative amplitude of finite duration depending on application. In our case, we generally consider it as 1 is represented by positive amplitude, 0 is represented by negative amplitude. Yes, good evening Rutuja. So because as you understand that it is the crash course, so we have to limit our discussion to the certain point, right? So that is why we are not going to the actual block diagram of the digital communication, and after the block diagram of digital communication I teach you the block diagram of the pulse code modulation. So I started directly from the pulse code modulation because our very important topic is pulse code modulation. So we have drawn the transmitter and we have to just discuss the transmitter part in the first chapter. We don't need to we don't require the channel and we don't require the receiver. So we will only constrain limit our study in the transmitter side. So our first topic is sampling theorem. So in the sampler we are having the first topic, which is sampling theorem. Sampling theorem, which is very important. So what it states? So it states that a signal which is band limited to FM, a signal which is band limited to FM hertz, that is highest frequency component is FM. Highest frequency component is FM. Whenever a band limited signal is given, it means that it is having the highest frequency FM. So a signal which is band limited to FM means it is having the highest frequency FM. So a signal which is band limited to FM hertz can be completely recovered from its samples, if samples are taken, if the samples are taken at the interval of Ts less than equal to 1/2 FM or at the rate Fs greater than equal to 2 FM. So this is the condition these are the two conditions by which we can calculate the sampling frequency. So sampling theorem states that a signal which is band limited to FM can be completely recovered from its samples if the samples are taken at the interval. So when you collect the sample, the gap should be considered according to this particular relationship. Okay, so the Ts is less than equal to 1 upon 2 FM. And the sampling frequency, this is called the sampling frequency and sampling interval. Okay, so it is sampling frequency and it is called sampling interval. Sampling interval. So whether it can be asked for sampling frequency and sampling interval. Yes, Shri Krishna, thanks. Okay. Now, how to perform this sampling? So to perform sampling, we multiply the signal to be sampled by, we multiply the signal MT which is to be sampled by a sampling function. Whenever you want to sample any signal, multiply it by sampling function, and the sampling function is generally given by this train of impulse. The sampling frequency is given by train of impulse. This is called S of t. Sampling function is defined by S of t. Okay. So it is defined by the S of t, and the sampling function is nothing but train of impulse, and the message signal is, suppose this is the continuous amplitude signal. So the same signal, let's consider this m of t. So whenever you want to sample any signal, multiply the signal which is to be sampled by sampling function. When you will multiply the signal by sampling function, what you will get? So according to this particular diagram, this is the sampling function S of t, and this S of t and this y of t, this m of t and S of t are multiplied. So m of t multiplied with S of t we will get. So this ms of t is called sampled signal. It is called sampled signal. So whenever you multiply the signal by train of impulse, you will get the sampled signal, and to achieve this particular theorem, we have to consider the sample in the interval of Ts. So to collect the sample in the interval of Ts, we have made this train of impulse at the interval of Ts. So when you multiply this sampling function by this message signal, what you will get? So when you will multiply, you will get the signal in the form of this 0, you will get this 0, and the next signal will be after Ts, you will get the signal at 0, because here at the 0 we are having the impulse function. So this impulse will be multiplied with the message signal, and from the property of the impulse, we know that whenever you multiply any signal with the impulse signal, we will get the signal at t equal to 0 and the impulse itself. So whatever will be the amplitude of this message signal, we will get here in the form of impulse function, because it is m of 0 into delta t. So m of 0 into delta t, it means we will get the signal at 0. Now from 0 to ts, the signal is 0 here. So the 0 will be multiplied with this, so the signal will be 0. And ts, we are having the impulse again, so we will get the amplitude again at ts, and again we will get the impulse at 2ts, and so on, and then 3ts. Okay, so the shape will be like this only. The shape of the message signal will remain same. The shape of the message signal will be same as this. This is the shape of the message signal, and here also if we will connect all the amplitudes, we will get the same shape. But actually we are having amplitude only a certain time, which is t equal to 0, we are having m of 0. At t equal to ts, we are having m of ts and delta t minus ts, and so on. So this is equivalent to replacing t by nts, replacing t by nts in the signal. So tell me whether up to this point it is clear or not. Up to this point it is clear or not, tell me. Okay. Okay, fine. So let's write the expression of this sample signal. So this ms of t is m of t, and the train of impulse is represented by summation n is equal to minus infinite to infinite delta t minus nts, delta t minus nts. This is the train of impulse. Train of impulse is represented by this expression. When this message signal is multiplied, with impulse from this property, if it is shifted to any particular time, we will get the signal at t is equal to ts, because the impulse will exist only at ts. So similarly here the impulse will exist at nts. So we can write m of nts and then delta t minus nts. So this is the expression of sampled signal. This is the expression of this signal, ms of t. This is the expression of this signal which we have drawn here. Because when you substitute n is equal to 0, you can see that when you substitute n equal to 0, so at n equal to 0 you will get m of 0 and delta t. So here it is nothing but n equal to 0, m of 0, and here delta t will be there. And when you will substitute n is equal to 1, you will get m of ts and delta t minus nts. So m of ts, you can see here m of ts we are getting at n is equal to 1. So if you will substitute n is equal to 1, 2, 3 and so on, you will get the signals like m of 2ts, m of 3ts. Okay, so this is the expression of this particular diagram, which is the sampled form of the message signal. It is the sampled form of the message signal. Okay. Now, next is, as we have written here, m s of t is equal to m of t and s of t. S of t is a sampling function. Okay, so the s of t is a periodic signal actually. Sampling function is always a periodic signal with time period Ts. Okay, so S of t is a periodic signal with time period Ts. So any periodic signal can be represented by its Fourier series. So periodic signal can be represented by, the periodic signal can be represented by Fourier series. Okay, so the Fourier series representation, no, there will be no noise after sampling, because until you transmit the signal through the channel, you won't get noise mostly, because we don't consider the noisy signal in the input side. When you transmit the signal through the channel will add some noise in the signal. That noise only we consider. The other noise that might be generated in the transmitter side itself, like because of the temperature of the device, it may be possible there will be some thermal noise. So all those noise we don't consider in our study. In practice, there will be some noise, there may be some noise, thermal noise, Johnson noise, short noise, natural, because of the natural behavior of the devices, the noise may come, but the noise will not be considered in the transmitter side in our study. Channel is wireless in digital communication. The channel can be wired and wireless in digital communication. In our first chapter, that is your baseband transmission, the channel is wired. Because we are not modulating the carrier signal, the signal cannot be transmitted without modulation. We know that the signal cannot be transmitted by the antenna without modulation. If you have studied the modulation in our starting lecture of the course, I told that why the modulation is required. So modulation reduces the height of antenna. So if you want to transmit any signal wirelessly, you have to consider the antenna, and if you don't consider the modulation, the height of antenna will be very much high, which is not practically feasible. So here we are not modulating, that means we have to transmit the signal by wired medium, that is by optical fiber or coaxial cable. The difference between short noise, natural noise, that is not our point of study right now. Okay, we don't need to study all those theoretical topics. Natural noise may be from the thunderstorm, etc., because of the fog, etc., and the short noise because of the thermal temperature that might be generated inside the device. So all these things we don't need to study. The noise, because of noise the error will come. Noise and error are different. Because of noise present in the channel, the error will come in our signal. Noise and error is not same. Okay, so I was telling that this S of t is a periodic signal, so it can be represented by Fourier series, and the Fourier series representation of this S of t is 1 upon Ts summation 1 upon Ts plus, let me write the trigonometric Fourier series form so that you will understand this, why I will get the signal in this form. N is equal to infinity and cos n omega st plus bn sin n omega st. Okay, so this will come from the signal Fourier series, and I hope you know the Fourier series. Okay, so to calculate the periodic signal S of t, to represent the periodic signal in the form of Fourier series, we have to write this a0 and an and bn, and because the sampling function is a even signal, it is symmetrical about y axis, the bn value will be 0. So this bn is 0 for even signal, and because the sampling function which we considered, which is train of impulse, is an even signal, that is why the bn will be 0, and when you calculate an you will get 2 by ts. So when you substitute this value you will get 1 by ts, and summation n is equal to 1 to infinite, this is 1 by ts and cos of n omega st. So this is the trigonometric Fourier series of train of impulse. This is the trigonometric Fourier series representation of train of impulse. So now you will substitute this value here. So this is ms of t equal to m of t, and in the bracket we will be having 1 by ts plus 1 by ts summation n is equal to 1 to infinity cos of n omega st. So when we substitute all the values and multiply with the message signal mt, we will get mt by ts, and when we substitute n is equal to 1, we will get here, yes, here it is 2 by ts. Okay, here it is not 1 by ts, it is coming out to be 2 by ts. So here we will get mt into 2 cos omega st divided by ts, and 2 mt cos of 2 omega st divided by ts, and so on. So this is the expansion of the sampled signal. This is expansion of the sampled signal. Suppose I take the Fourier transform. If I take the Fourier transform, okay, here we are taking the Fourier transform. So what is the Fourier transform of the message signal mt? So let us say the message signal mt is having the Fourier transform m of f. M of t is having a Fourier transform m of f. Okay, so we are assuming that this mt is having a Fourier transform m of f, and this mt into cos omega naught t will be having a Fourier transform what? 1 by 2 m of f minus f naught plus m of f plus f naught. This is the Fourier transform of mt cos omega naught t. So here also we are having mt and cos omega st. So it is having the Fourier transform, which is nothing but a modulation property. But the 2 is already multiplied here. So when you multiply the 2 here, this cross multiplication of these 2. So when you multiply 2 here, this 2 will get cancelled and you will get this as Fourier transform. So here also you will get the Fourier transform 1 upon ts, and in bracket m of f minus fs plus m of f plus fs. Similarly, here also you will get 1 upon ts common, and here the frequency is 2fs. Here the frequency is fs. Here the frequency is 2 times fs. So it will be m of f minus 2fs plus m of f plus 2fs, and so on up to infinite. Is it clear up to this point? Okay, so any point if you are having doubt, you can ask. At any point if you are having doubt, you can ask, because in digital communication you might have many doubts, so you can ask those doubts. What we are doing is just we are multiplying the message signal with the sample signal, and the sample signals are actually a periodic signal. So because the sampling signal is a periodic signal, any periodic signal can be represented by Fourier series, and if it is represented by Fourier series, the Fourier series expansion I am assuming directly. Okay, I am assuming that you know the how to calculate the Fourier series. The shifting is already done, Raju. The shifting, what about shifting means? The shifting has already been done here. Whenever the message signal is multiplied with the cosine signal, the spectrum of the message signal, that means the Fourier transform of message signal, shifts to the frequency by which you multiplied. So we have multiplied with the frequency fs, we have multiplied with the frequency 2fs. So the original spectrum m of f will shift to the plus fs and minus fs. So this is my plus f naught and minus f naught. Similarly, if you multiply with the 2fs, it will shift to the plus 2f naught and minus 2f naught. Okay. Now, if you will see that this m of f is having all the components and 1 upon ts is common, 1 upon ts is common in all. So we can take this 1 upon ts common, and can we write like this: n is equal to 0 to infinity, or sorry, minus infinity to infinity, m of f minus n into fs. So can we write this expression in this form? Just check once. Can we write all these terms in the form of summation? Suppose I substitute n is equal to 0 in this expression, I will get m of f upon ts. Our first term will be justified. If I substitute n is equal to 1, we will get m of f minus fs divided by ts. Our second term will be justified. If I substitute n is equal to minus 1, I will get m of f plus fs divided by ts. Our third term will come. So in this way, all the terms can be represented in the form of summation, when the summation is varying from n is equal to minus infinite to infinite, because this is up to the infinity. So for plus minus 1 we will get these two terms, plus minus 2 we will get these two terms, plus minus 3 we will get all more terms, and for plus minus infinity also we will get terms. So that is why the n is ranging from minus infinite to infinite. And always remember that this 1 upon ts can be written as fs. Okay, the frequency is nothing but 1 upon time period, 1 upon ts. So this 1 upon ts can also be denoted by fs. Fourier transform from Fourier series. Yes, from Fourier series we are taking the Fourier transform. Why we are considering the Fourier transform? Because we want to see that why the statement says that fs is greater than equal to 2fm. So because in the statement we have the information about the frequency of the sampling, so that is why we are considering that how do we get this sampling frequency. So to get the sampling frequency we need Fourier transform, because after taking the Fourier transform the signal will be shifted to the frequency domain. So once we get the frequency domain signal, we can see that what is the role of the fs. Fs means sampling frequency. No, Asif, there is no analog communication, noise in analog communication in our syllabus. Okay, so in our syllabus, you don't need to study about the noise in analog communication. You may get some question in the test series, in the different test series, but there is no need to study about those topics because it is not coming since 10 to 15 years in GATE, so it is not an important topic, and actually it is not mentioned in the syllabus also. So this expression is very, very important. Whatever the sampling method we used is called instantaneous sampling or ideal sampling. Whenever there is a word written in the question that ideal sampling or instantaneous sampling, it means that the sampling function is train of impulse. So in the 90% of the question you will get the train of impulse as a sampling function. That means in the 90% of the questions we will be having ideal sampling or natural sampling or instantaneous sampling, not natural sampling, ideal sampling or instantaneous sampling. There are two other types of sampling which is known as natural sampling and flat top sampling. That is only the 10% of the weightage of the overall sampling. So 90% time we will be having the ideal sampling. So that is why we will only discuss the ideal sampling. And when the sampling function is other than train of impulse, what we have to do is, I will tell in the form of question. We don't use frequency in omega. You can consider in omega domain also. I am comfortable with the frequency domain. That's why I always consider the F. Okay, Nutan. So your doubt will be now going to discuss. Okay, so this is the expression of the ideal sampling. So whenever you perform the ideal sampling, you will get this expression. Now what will happen? Suppose the message signal MT is having a Fourier transform M of F. Okay, so if it is the message signal, and if I am assuming that its Fourier transform is a triangular signal which is minus FM to FM. So because we have already said that when we sample the message signal, it should be band limited to FM hertz. And also in the statement I had written that the band limited to FM means the spectrum should have maximum frequency FM. So you can see that in the diagram, the message signal is having maximum frequency FM, and after FM it is 0, and here also in the negative side it is having the maximum frequency minus FM. So whenever the positive spectrum is coming, the mirror image will be coming in the negative side. So if the signal is band limited to FM hertz, it means that it is having a highest frequency FM. It is having the meaning that it is band limited to FM. So it will not be having any component greater than FM. So after FM it should be 0. Then only we can call it as band limited. Yes, thank you for enjoying the English session. Okay. So be regular in the class so we can have the more interactive session. Okay. So have you got this point? We are assuming that the spectrum of the message signal is M of f. Spectrum of message signal is M of f. Now we are considering that case 1, okay, case 1, that is called oversampling. Case 1 is called oversampling. Oversampling is the case when the fs is greater than twice of fm. Oversampling is the case where the fs, the sampling frequency which you select, is greater than twice of the message signal frequency. So twice of the message signal frequency. So let us say let fm is equal to 5 kilohertz. Fm, we are assuming just fm is having the frequency 5 kilohertz, then what should be the value of fs? So according to this case, fs should be greater than twice of 5 kilohertz. That means fs should be greater than 10 kilohertz. Okay, so fs should be greater than 10 kilohertz. Say fs is equal to 15 kilohertz. If I assume fs is equal to 15 kilohertz. Okay, so we are having both the frequency. We are having the message signal frequency 5 kilohertz. We are having the sampling frequency 15 kilohertz. And according to this 15 and 5 kilohertz, we will draw this particular expression because it is in frequency domain. So we need the frequency. So now we have to draw this particular expression. We have to draw this particular expression. So let's draw this particular expression. This is ms of f. We are going to draw. When I substitute n is equal to 0, when I substitute n equal to 0 here, we will get 1 upon ts into m of f. So m of f means this shape. M of f means this shape. So we will get this particular term, this particular component, and it will be ranging from -5 to 5 and having the amplitude. Let us say the amplitude is 1 here. Let us say the amplitude is 1 here. So the amplitude will be 1 upon ts times of 1. So at this point the amplitude will be 1 upon ts. Is it clear or not? We will get for n equal to 0. Yes, I have written here, assuming fs is equal to 15 kilohertz. We have to select the fs greater than 10. Any value greater than 10 you can select. For convenience, I am taking in the multiples of 5. Okay, so 15 I am considering. You can consider 11, 12, 13 and so on. Overlapping of the signals. No, Mayuri, not overlapping. There will be no overlapping. Okay, is it clear at this point? Why I got this shape? Because we have assumed that the message signal is having the Fourier transform like this. Now, suppose I consider n is equal to 1. So if I consider n is equal to 1, I will get 1 upon ts and m of f minus fs. So m of f minus fs means 1 upon ts m of f minus 15. because the fs we have assumed is 15. So what is the meaning of m of f minus 15? M of f minus 15 means it will shift to the 15. The spectrum will, the component which is at 0 will shift to the 15. So it will be 10 and it will be 20. And the amplitude is same. The amplitude, you can see that both are having amplitude 1 upon Ts. So 1 upon Ts times of maximum value. Is it clear? Centered at 15 kilohertz. So when m of f minus 15 is written, it means that our original spectrum, which is triangular shape, will shift to the 15 kilohertz. Okay, so it will shift to the 15 kilohertz. Now when I substitute n is equal to minus 1, suppose I substitute n is equal to minus 1, I will get 1 upon Ts m of f plus fs, and fs is 15, so 1 upon Ts m of f plus 15. So it will shift to the minus 15 because it is advanced operation. So advanced operation means we will get the spectrum here at minus 15, and it will be minus 20, and it will be minus 10, and so on. This is for n is equal to minus 1. And here also we will get more terms, and this axis is in kilohertz. So is this diagram is clear? Is it clear to everyone? So what we are observing is, if there is a overlapping, there will be a gap between the original spectrum and its replica. This is the original spectrum. This is original spectrum means this is our message signal. This is our message signal. You can see that for n equal to 0, we get m of f, and when you get m of f, when you take inverse Fourier transform, you will get m of t. So m of t is the actual message signal that we want to recover. Okay. So for n equal to 0, you will get original signal, and for n equal to 1 minus 1, you will get replica of image, replica of original signal. Okay, these all are the replica of original signal. So in case of oversampling, with the help of this example, we observe that the original spectrum and its replica are separated by some band. They are separated by some frequency. They are separated by some frequency. So there will be no overlapping. So in this particular case, no overlapping. Okay, because there is no overlapping in the original spectrum and its replica, we can easily recover our message signal, because this original spectrum is separated with its replica. We can easily recover this message signal. So which filter we should use? Which filter we should use to recover our message signal? Please comment. Which filter we should use to recover our message signal? Yes, low pass. Low pass because it is centered at origin. Whenever the signal is centered at origin, it is recovered by low pass filter. Okay. So we want to recover this particular spectrum. So here we can use a low pass filter to recover our message signal. No band pass filter, Shivani. The frequency component which is centered at origin should be recovered by the low pass filter, because the low pass filter is the filter which is having cutoff frequency FC can pass the frequency component less than FC. So you have to use low pass filter whose cutoff frequency is FM. Because the cutoff frequency is FM, it will pass the frequency component which is less than FM. So it is less than FM, so it will pass the spectrum. Okay, suppose we want to recover this signal, then because it is centered at frequency which is other than 0, whenever the frequency component is centered at other than 0, we call it as band pass signal. So the band pass signal is recovered by band pass filter, but the low pass signal is recovered by low pass filter, and our message signal is always a low pass signal. So this low pass signal will be recovered by low pass filter. Is it clear? Okay. Now, what is the difference between the practical and the ideal low pass filter? So the ideal low pass filter is having a sharp cutoff frequency. So this is the filter which we have drawn here is having a sharp cutoff frequency. So the low pass filter and the practical low pass filter and the ideal low pass filter. This is the ideal low pass filter. Okay. So it is ideal low pass filter. If I say ideal low pass filter, it means it is a rectangular pulse symmetrical about origin and having some cutoff frequency like FC. Okay. And the band pass low pass filter, practical low pass filter, the practical low pass filter will be like this. It will not be having a sharp cutoff frequency. It will be having the shape like this. Okay. So how do you decide the cutoff frequency? Here the gain is 1, suppose. So here also the maximum amplitude is 1. So when the frequency at which the maximum amplitude becomes 1 by root 2 times. So what is the 1 by root 2 times of 1? So 1 by root 2 times of 1 is nothing but 0.707. So the frequency at which the amplitude is 0.707 is called cutoff frequency. Okay. So the difference between the ideal low pass filter and the practical low pass filter is the ideal low pass filter is having a sharp cutoff frequency, and at the cutoff frequency there will be sharp transition, and in case of practical low pass filter there will be a gradual transition. So from 0 to 1 it is slowly increasing from 0 to 1 and 1 to 0. But in case of ideal it is abruptly increasing from 0 to 1 and 1 to 0. So how do you define the cutoff frequency for practical low pass filter? So the cutoff frequency is the frequency at which the amplitude becomes 1 by root 2 times of maximum amplitude. So if the maximum amplitude is 1, So 1 upon root 2 times of 1 is 0.707. So the frequency where the amplitude is 0.707 will be called as cutoff frequency. Yes, 3 dB frequency. We don't want to recover this signal Newton, so there is no need of using band pass filter. We only want to recover our original signal. Can be recovered by practical low pass filter. Yes, in this time we can recover by practical low pass filter. See, now I am going to draw the spectrum in general. When we draw just now, we consider some value. So by considering the value with this condition, okay, by considering the value of sampling frequency, by this condition we observed that the original spectrum and its replica will be separated. So now I am drawing the diagram by general case, in general case. Yes, Akansha? So in general, if I draw it in general, so when we substitute n is equal to 0, I will get this Fm. So last time when I draw the diagram, I consider it from -5 to 5, and this is nothing but the message signal frequency. So it will be from -Fm to Fm, and the height will be 1 upon Ts. Okay, and now it will shift for n is equal to 1. The amplitude should remain same. It will shift to the Fs. That particular value was considered as 15. So in general it should be sampling frequency, and it should be Fs plus Fm and Fs minus Fm and so on up to infinity. Now it is minus Fs minus Fm and minus Fs plus Fm. And so on. N is equal to -1, and this is for n is equal to 0. Okay, tell me whether this diagram is clear or not. Whether this diagram is clear or not. So we are drawing the diagram for the same case where Fs is greater than 2 Fm. So whenever the Fs is greater than 2 Fm, we will be having the original spectrum which is separated by its replica. Separated by its replica. Okay. So in this particular case, we can see that we can put practical low pass filter. We can substitute the practical low pass filter to recover our message signal. To recover our message signal, we can substitute the practical low pass filter. Okay. Okay. So this is the cutoff frequency will be somewhere here. All right. Now, because the original spectrum and its replica are separated by the gap or the band, because of the gap, we are able to use the practical low pass filter. So actually it is protecting our original message signal from its replica. Because of this band gap, this replica is not overlapping with this original spectrum. Okay, so this is original spectrum and this is replica. So because of this band gap, this original spectrum is not overlapping with its replica. So that is why this gap is called guard band. This gap is called guard band. So what is the value of this band? So guard band is highest frequency is Fs minus Fm. This is the highest frequency. How to calculate any bandwidth? So the bandwidth is calculated by highest frequency and the lowest frequency. In this range, the highest frequency is Fs minus Fm and the lowest frequency is Fm. So this is Fs minus 2Fm. So the guard band is Fs minus 2Fm. Okay, so have you got this point? Thank you, Laksh. Fine. Now the case 2. Now case 2. That is called critical sampling. And mainly the Nyquist rate. The terminology which we generally use for this particular case is Nyquist rate, not the critical sampling. Okay, so the Nyquist rate is more popular terminology where Fs is exactly equal to 2Fm. Fs is exactly equal to 2Fm. So in the last diagram, substitute Fs is equal to 2Fm, you will come to know what should be the diagram. In the last diagram, for the case 1, substitute Fs is equal to 2Fm, you will get the spectrum. Okay. So substitute Fs is equal to 2Fm. When you will do this, you will see that you will be getting the spectrum like this. This is 0 to Fm and minus Fm, it will remain same. And when you substitute Fs is equal to 2Fm, the minimum value was Fs minus Fm. So when you substitute Fs is equal to 2Fm, you will get 2Fm minus Fm, so that is Fm. So now it will start from Fm, and this value is Fs, and this value is Fs plus Fm, and again you will get a spectrum like this, and so on. This is 2Fs. Guard band will be 0 now. Yes, exactly, Mayuri. Guard band will be 0 now. So we will get the spectrum in this form. This is 1 upon Ts, and this will be for n equal to 0, this will be for n equal to 1, this will be for n equal to 2, this is for n equal to -1, this is for n equal to -2, and so on. And this is the frequency axis. Okay, so is it clear? Yes, exactly. Ideal low pass filter will be required now. Fine. Okay. So in this particular case, if you want to recover your message signal, you need a ideal low pass filter. If you want to recover message signal, you have to consider ideal low pass filter, because when you use practical low pass filter in this case, it will overlap with this. If you use the practical low pass filter, so it will also pass this replica. Some portion of the replica will also pass. So this replica should not be passed through the low pass filter. So that is why the ideal filter is used. Ideal low pass filter will be used in this particular case 2, which is the Nyquist rate, Fs is equal to 2 Fm. Okay. So that is why practically we always keep the sampling frequency greater than 2 Fm. As you have seen that when Fs was greater than 2 Fm, the original spectrum and its replica was separated. When you reduced the value of Fs to Fm, its replica is moving towards the original spectrum. That is why the gap is reducing and the gap become now 0. So when Fs is less than 2 Fm, what will happen? When Fs is less than 2 Fm, what will happen? Nutan, I hope you have got the answer that what is the problem with the low pass filter. Have you got the point? It will also pass the other frequency component. So if it will pass the extra frequency component, we only want the message signal frequency. So that is why we don't use the practical low pass filter here. Overlapped aliasing will occur. Yes, distortion will occur. Exactly. Okay, so in the case of Fs less than 2 Fm, as we have seen that when Fs was greater than 2 Fm, the message signal spectrum and its replica was separated. When Fs is exactly equal to 2 Fm, when Fs is exactly equal to 2 Fm, the spectrum and the replica is approaching towards the original spectrum. Now you are making the sampling frequency, third case, this is case 3, which is Fs less than 2 Fm. it is called undersampling. So undersampling, when the fs is less than 2 fm, the replica will be approaching towards the original spectrum, and when it approaches to the original spectrum, it will overlap with the original spectrum. Because it is moving towards the original spectrum, it will overlap. When it will overlap, it is called aliasing effect. So somebody was asking me about the aliasing effect, so I hope now he or she got its point. So here we will get the fm, it is same as fs, it is same as minus fs, and it is minus fm. So we are considering the distortion here. The highest frequency component of the message signal, the highest frequency component of the message signals are distorted. Okay, so this effect is called aliasing effect, aliasing or fold over error. Okay, so how can you define the highest frequency component of message signal is distorted by its replica. Okay, so aliasing is defined. How can you define? So aliasing is nothing but when the highest frequency component of message signal is distorted by its replica, it is called aliasing. So why I am calling highest frequency? Can anybody tell why I am calling it as highest frequency? Because the original message spectrum is represented like this. This is minus fm and fm. So highest frequency means the highest frequency of this message signal is near about fm. The message signal can have the highest frequency fm, and the portion which is distorted is near to fm. The portion which is distorted is near to fm, and fm is the highest frequency which is present in the message signal. That is why I am saying the highest frequency component of message signal is distorted by the replica. Then it is called distortion, aliasing. Yes, so if you have not liked the video yet, so like the video so that it can reach to the 150 in the session itself. It has been reached to 129. So like the video and make it 150. Make it 150 in the session itself. So is it clear to everybody? Up to this point, is it clear? Thank you, Nutan. Those who have liked before the session, so much appreciable. Okay, so up to this point it is clear to everyone. Now let's discuss about a sinusoidal signal. Okay, in the present discussion we considered that the message signal MT, in the present discussion we consider the message signal MT is having Fourier transform M of f, and this M of f is having a shape that is a triangular signal. Is it okay? And the amplitude was 1. Is it okay? We consider in the last discussion that the message signal is band limited to FM and its shape was assumed as triangular. Yes, thank you Shivani, and thank you all to make it that you made it 131. Yes, Shri Krishna, you always try to keep like more than 10 plus from your side. Okay, now you have got this point. Now we are saying that suppose message signal is sinusoidal. Okay, message signal is sinusoidal, AC AM cos omega mt. When the message signal is sinusoidal, what will be the Fourier transform? Tell me. Now you should tell me, you should be able to tell me the Fourier transform of this mt. If the message signal is sinusoidal, then what will be the Fourier transform? The number of likes are reducing now, so I think somebody is now taking its like back. So it was reached to the 131, now it has been reduced to 129. So anyone who wants to take their like back, you can take, no problem at all. Yes, shifted impulse. Yes, very nice. So can we make it 100? Because it is now 128. So if you want to take your like back, so make it 100. Why to make 150? Let's make 100 now. Okay. So the message signal MT is having a Fourier transform M of f that is equal to 1 by 2. Yes, so we will get the impulse and the frequency is plus minus fm, so del f minus fm and del f plus fm. No, it was reached to the 128, now it is coming back to the 133. Okay. Okay, so M of f, if the M of f is the impulse function, this M of f, when this M of f will be taken, so it is impulse at plus fm and impulse at minus fm, and the amplitude here is am, so the amplitude will be now am by 2. So here we can write this am by 2. Is it clear? Is this Fourier transform representation is clear to you? Yes. Okay. So now let's draw it for Fs greater than 2Fm. Now draw Ms of F for Fs greater than 2Fm. Okay, I am giving you one question, that draw the Ms of F, which I have already written here. You have to draw this particular expression for this case. You have to draw it for this case. This we have done. Okay, M of F Fourier transform, which is having the triangular shape, we have already drawn. So now draw it for Fs greater than 2Fm. No need to find signal power right now, Nutan. Yes, oversampled, but what you will get? What you will get, you can tell me, I will draw. Okay, tell me what you will get when you draw this spectrum, what you will get. Oversampling, that is okay, oversampling is okay. I am saying what you will get when you draw the spectrum. So this Ms of F, yes, exactly, Nilanjana has given the exact answer which I wanted. So everybody can read it, read her chat. So you will come to know what I wanted to ask you. So when you substitute n is equal to 0, when you substitute n equal to 0, you will get 1 upon Ts and m of f, right? 1 upon Ts, m of f. So this is the m of f. So you will draw the spectrum. So you will draw the spectrum at Fm and at minus Fm. Okay, so I am not writing exact amplitude. Okay, if you want me to write, I will write also. So we will get Am by 2Ts. Okay, so Am by 2 was there, and the amplitude is multiplied by 1 upon Ts. So we will get Am upon 2Ts. And when you will substitute n is equal to 1, these two are for n is equal to 0. Okay, so these two is for n equal to 0. When you substitute n is equal to 0, you will get these two impulse, which is the original impulse. Now when you will substitute n is equal to 1, so n is equal to 1 means 1 upon Ts m of f minus Ts. So m of f minus Ts, what does it mean? F minus Fs, what does it mean? So it will shift to Fs. So it will shift to Fs, suppose somewhere here, and you will get impulse at Fs minus Fm, and you will get impulse at Fs plus Fm, and it is for n is equal to 1. N is equal to 1. Similarly, when you substitute n is equal to minus 1, you will get 1 upon Ts m of f plus Fs, m of f plus Fs. So m of f plus Fs means the impulse will shift to Fs. that is sorry, minus fs, it will shift to minus fs. So here we will get minus fs plus fm, minus fs minus fm. It will be for n is equal to minus 1. So it will go up to infinity, it will also go up to infinity. Is it clear to everybody? Is it clear to everybody? Yes. So now my next question is, if I ask you what are the frequency component present in this signal, then what will be your answer? If I ask you what are the frequency component present? What are the frequency component present? Frequency component present. What are the frequency components present? Tell me, what are the frequency components present? Frequency I am asking, Shri Krishna, frequency component. Manvendra, I am not asking how many, I am asking what are the frequency component present. Nilanjana, your answer is incorrect bit because you have missed one frequency component. So the frequency component which are present, we only consider positive frequency. So as you can see that what are the frequency we are getting. So because frequency is always positive, we will only consider the positive side. So we will get this, because the component is present at Fm, the component is present at n equal to 1 Fs minus Fm, the component is present at Fs plus Fm. So if I ask you then what are the frequency components are present, then its answer is Fm, Fs plus minus Fm and 2Fs plus minus Fm. If I would have drawn for n equal to 2, so n equal to 2 we get m of f minus 2Fs divided by Ts. So it will shift to 2Fs. So there will be some component at here also centered at 2Fs and one is at 2Fs plus Fm and another is at 2Fs minus Fm. So here at this point also we get the spectrum or component. So in this way we can calculate the frequency component. So number of terms will be infinite, but what are the terms? So these terms are like this, and this is for sinusoidal signal. Especially you can see that we have exactly exactly see these frequency components we are getting for sinusoidal signal. So whenever we sample the sinusoidal signal, whenever it is sampled, the frequency component are given by this. Okay. So are you able to listen me now? So tell me whether you are able to listen me. Yes, clear now? Yes, it is working right now? Fine. So the last point that we are going to discuss is, we are saying that, okay, so we were saying that frequency component present in sampling of single tone message signal, as we sampled the message signal mt, which was am cos omega mt. So this is a single tone signal. So this is a single tone signal. So whenever you sample the single tone signal, you will get the frequency component like this. Okay? Is it okay? So have you got this point? Sampling of single tone. Sampling of single tone. Sampling of single tone. Now, if message signal is multi-tone, if message signal is multi-tone, that is m of t is equal to a1 cos 2 pi f1t plus a2 cos 2 pi f2t and so on, then in this case, in the case of multi-tone, the sampling frequency is given by 2 times maximum frequency component present in message signal, like bandwidth of AM, In case of AM signal, how do you calculate bandwidth in case of multi-tone? So in case of multi-tone, we calculate the bandwidth which is twice of maximum frequency present in the message signal. Similarly, the sampling frequency we calculate for multi-tone signal, which is twice of maximum frequency component present in the message signal. Is it clear? Is it clear or not? The sampling frequency will be twice of message signal frequency, twice of maximum frequency present in the message signal. So if f1, f2, f3 and so on, so the maximum will be given by 2 times of maximum of how many frequencies are there? So there can be more than one frequency. So if there are more than one frequency, so find the maximum value of all the frequency and multiply it by 2, you will get the sampling frequency. So we will see how it comes 2 times of maximum frequency, that we will see with the help of example in the next class. But right now just write that the maximum frequency of the message signal, twice of that will be the sampling frequency. Now for multitone, what are the frequency components present? Frequency components present in sampling of multitone. What are the frequency components present in sampling of multitone message signal? So now we will say that the message signal frequencies are present. So whatever will be the message signal frequency, all will be present, and the sampling frequency fs plus minus fm will present, twice of fs plus minus f1 will present, similarly and so on. Similarly, fs plus minus f2 will present, 2fs plus minus f2 will be present, and similarly fs plus minus f3 will present, and 2fs plus minus f3 will present, and so on. So these are the frequency component which will be present in sampling of multitone signal. When you sample the multitone signal, you will get these many frequency components. As we have seen for the single tone, in case of single tone the message signal frequency was present. Similarly, in case of multitone, all the frequency component of message signal will be present. So message signal having frequency f1, f2 and then f3 and so on. So all the message signal frequency will be present, and because of this term f of f minus nfs, we will get the multiple of fs. So we will get the multiple of fs, 2fs, 3fs, 4fs and so on, and plus minus message signal frequency, because here also we get fs plus minus message signal frequency was fm. So we got fs plus minus fm. Similarly, here also fs plus minus f1, fs plus minus f2, fs plus minus f3. So all these frequency components will be present if there is more than one frequency component in the message signal, that is the multitone case. So whenever the multitone case is given, these are the frequency component that will be present after sampling. After sampling, you will get these many frequency components. Is it clear? Avinash, we will see in the question, in that type of how to solve that type of question. Your question will be clear tomorrow. Okay, so let's end up the today's session. So that is all for the today's session, and we will be discussing, or we will be solving the questions from the sampling tomorrow. Okay. So the kind of question that is asked in GATE, that will be covered tomorrow. So I hope you liked the video. Okay, so you enjoyed the session, and tell your friends to come in the digital communication class. Those who are facing the doubts in digital communication, they should come in the class. Okay, so tomorrow we will be solving all the questions related to these topics. Yes, sampling means same. Sampling everywhere will be same. So there will be no change whether you study it in digital communication or you study it in sampling. The sampling means nothing but the discretization in time domain. Thank you, Sailesh. Love you, dear. Thank you for so much love and appreciation you always put here. So keep sharing the videos, and keep liking our videos, and keep supporting us, so that we can give you more and more content with more motivation. Okay, because the motivation is always required from your side. When you motivate us, we will be able to provide you very good content in future also. Okay, so let's finish up the session. We will meet tomorrow at the same time. Thank you. Love you all. Good night.